Hey guys, so with empirical and molecular formula, I'm starting to really regret giving you all of these notes because after trying it with first period and fourth period on Tuesday, it seems like all of this, it's just so many words and things like that, so we kind of really need to simplify it. So if you wouldn't mind just finding a blank piece of paper, I think the very back of your packet is blank, but you could also write it in the margins. The main thing that I want you to know is the relationship between empirical formula and molecular formula. So empirical formula is a simplified version of the molecular formula, which I'm going to abbreviate as MF. Okay, empirical formula will be EF. Right. Now, molecular formula is the actual formula. Now, you might wonder why we need an empirical formula then, that sort of thing. This really plays into effect a lot with what we call polymers, so things that make up plastics and other large compounds, and molecules are often made up of repeating smaller things. So really, our molecular formula is equal to our empirical formula times N. And N is a ratio between the two. And so, for example, if we have the compound C4H6, okay, if this is our molecular formula, okay, we can see that the 4 and the 6 both have a least common multiple of 2. And so it can be reduced to C2H3. So that would be our empirical formula. And N would be 2, because that is what we were able to reduce or simplify those subscripts as. Now, oftentimes, N is calculated by looking at the molar mass of things. So if you were actually in a lab, which I'm going to try to draw you what I'm talking about, you would have this machine, a gas chromatography mass spectrometer, so gas chromatography mass spectrometer, so GCMS, and essentially what's inside a GCMS is there's a furnace, okay, it gets extremely hot, and inside the furnace are these coils, okay, and what you do is you inject a little bit of your unknown compound into the coil. And let's say you inject something, you don't know exactly what it is, it's this unknown, okay, but what happens is it gets superheated and it spreads out by mass, okay, so we know that what that means is the heavy atoms travel slowly. So heavy atoms are slow, smaller atoms are faster. So something like hydrogen, which only has a mass of 1.01, is going to travel a lot faster than carbon, which is 12.0. And when it spits out, there's at the very end of the coils, so I'll continue my picture of coils, it goes to this detector right here. This is the orange box, this detector. And what it does is it literally, as it spits out these superheated atoms, it counts them. And because they're separated by mass, it says, okay, it can determine it just counted 50 hydrogen atoms and 40 carbon atoms. And while it can't put the formula together, what it does is it spits out a percent composition. Okay, it spits out a percent composition. So it might be able to tell you that it is 40% carbon and 50% hydrogen and 10% oxygen, right? And so when it spits that out, what we can do is we can use that percent composition to determine the empirical formula. And if we knew exactly how many milliliters we put in before, or if we had to weight it, we would know the molar mass and we could calculate its empirical formula. Okay, and so with the empirical formula, there is a rhyme that goes with it. Rhyme is right here, and I was told that my rhyme doesn't actually rhyme, so why don't we go ahead and change that to poem. But the poem is percent to mass, mass to mole, divide by small, multiply till whole. And so for percent to mass, literally what you do is you change a percent sign into a gram sign. So that means 100% becomes 100 grams. So it's the easiest step. Mass to mole, we know mass is again referring to grams. And to mole, that means we need to do a one-step problem. You need to convert all of your grams of each element into moles, and that's gonna require the molar mass, which since it's elements, it's just using your periodic table. Divide by small, you divide each mole number by the smallest. Okay, so not too terrible. And then if after you have divided them, you don't get whole numbers, if you get numbers that end in 0.3, 0.5, or 0.7, you need to multiply till whole. Now, if you get a number that's 3.99, guys, that's a whole number. That's 4. If you get 2.02, that's 2. Okay, those aren't the type of numbers we're talking about. But if after the decimal your number ends in 0.3, 0.5, or 0.7, those are the ones that we're going to be dealing with, then you would multiply 0.3 times 3, 0.7 by 3, and that will give you a whole number. And 0.5 you would multiply by 2. So I'm going ahead and telling you what you need to multiply by. So if you can remember that, then you will be golden for your test and quizzes. So let's look at a sample problem. So if we look at number 1, it says, what is the empirical formula of a compound that contains 25.53% magnesium and 74.47% chlorine? Now we remember the first step of the rhyme is percent to mass, or percent to grams. So we're going to change 25.53% into 25.53 grams of magnesium, and we're going to change 74.47% into 74.47 grams of chlorine. And so that's step number 1. Step number 2 is to mass to mole. So I need to put each of these into their T-chart, and I need to convert from grams to moles. And so that means my grams of chlorine will go on the bottom, and I'm going to convert to moles of chlorine, grams of magnesium on the bottom to moles of magnesium. And if we look at the molar mass on the periodic table, we know that chlorine has a mass of 35.45 grams, and so that will be the molar mass, and it's equal to 1 mole. And then magnesium has a molar mass of 24.31 grams for 1 mole. And so when we take 25.53 and divide it by 24.31, we get 1.050 moles of magnesium. And when I divide 74.47 by 35.45, I get 2.101 moles of chlorine. Now remember, the third step is to divide by small. So if I look at these answers, 1.050 and 2.101, we divide by the smallest one. So I'm going to divide all numbers by 1.050 moles. Okay, and that will not only eliminate my my decimals, but this will also get rid of the unit of moles, and that's important because we're switching from percentages to grams to moles to just plain old atoms, like how many atoms or what's the ratio. And so this will be 1 magnesium, and then 2.101 divided by 1.050 will give us 2 chlorines. And so what we do is we just turn these right here that I'm highlighting in blue become our subscripts. And so we would write this as magnesium 1, but chemists are lazy, so I won't write that 1, Cl2. And that would be my empirical formula. Now, if we look at number 2, it says a compound with a molecular mass of 34.0 grams per milliliter, or excuse me, grams per mole, is known to contain 5.8% hydrogen, 94.12% oxygen. What is the molecular formula? Okay, so this one, I'm not going to have a ton of room down here, so I'm just going to move over to the side. And I recommend, guys, if you write in size 50 font, that you need to get some notebook paper and be working this out on a separate piece of paper, because these problems really work best if you have plenty of space to be able to keep your work organized. So if we come over here, I'm just going to go ahead and write down we had 5.88% hydrogen, and we had 94.12% oxygen, and we know that our molar mass, okay, so the molar mass of my molecular formula was equal to 34.0 grams per mole. So we're going to keep that information, and we're just going to keep on rolling. First thing is percent to mass. So I'm going to change these percentages into grams. So 5.88 grams of hydrogen, and then 94.12 grams of oxygen. So step number 1, done. Easy enough. Second step is to change it to moles. So we're going to put these in the T-charts. Remember, whatever's repeated, or whatever unit and thing we have up there is repeated down at the bottom. I'm going to put my grams of oxygen at the bottom, my grams of hydrogen. Oxygen's mass on the periodic table is 16.00 grams per 1 mole of oxygen. Hydrogen is 1.01, and that's for 1 mole of hydrogen. And when I divide these things, I'm going to get 5.82 moles of hydrogen and 5.882 moles of oxygen. And so the next step is to divide by small. So 5.82 is smaller than 5.88. So I'm going to divide by that. So 5.82 moles divided by both, 5.82 moles. And so this will give me 1 hydrogen. And when I divide this, I get 1.01, which that is close enough. That doesn't end in 0.3, 0.5, or 0.7. So I'm just going to round that off to 1 oxygen. And so that tells me that my empirical formula is HO. Right, so my empirical formula is that. But they didn't want to know my empirical formula. They wanted my molecular formula. Well, in order to do my molecular formula, we know that my molecular formula is equal to my empirical formula times N. Okay, so what we have to do is figure out, okay, well, what's N? Okay, because we know our empirical formula is HO, hydrogen, 1 hydrogen, 1 oxygen, but our N is something different. And so the way you calculate for N is equal to the molar mass of your molecular formula divided by the molar mass of your empirical formula. And they gave us the molar mass of our molecular formula. They told us it was 34.0 grams per mole. But we don't have the molar mass of our empirical formula. But luckily for us, we have a great chemistry teacher who taught us how to calculate molar mass. And so if we come over here to hydrogen and oxygen, we split up. We have one hydrogen, one oxygen. So we multiply them by their mass, 1.01, 16. That gives us this right here. And then we add them together, and we get 17.01. Okay, so that means our molar mass of our empirical formula is 17.01 grams per mole. And when I divide these two, I'm going to get 2. So it's a ratio of 2. So I'll multiply hydrogen and oxygen by 2 to get my empirical formula. And that will give me H2O2 as my final answer. Now, I know you're saying, Miss Nichols, this is a lot of work. I don't feel like doing all this, and I'm so sorry that you feel like this is a lot of work, but no way of getting around it. There's no way to make it shorter. This is about as short as it gets. So hopefully this was clear and will help you with your homework.